my opinion on this whole thing, and I was basically ignored. We'll keep doing things the way we keep doing things because the way we're currently doing things ensures online course quality.
Your opinion is very valuable to us.
Please leave a message after the beep.
Here's the opinion box.
And then the second beep right away. It's like beep, beep. Oh, sorry, we are running out of memory.
This is our opinion box. It's definitely not a trash compactor.
It looks like a trash can, but trust me, it's not.
It's not. We value your opinions here.
Yeah. Well, I kind of suspected as much, so it's no
Are we
big
doing
deal.
assembly language programming today?
No, I'm gonna check out my own channel to figure out where we stopped last time. Do you guys remember? Where did we stop?
We stopped right on the overview.
Stop sometime around 7:30.
8-bit memory unit.
So
Okay.
8:20.
Yeah, so we're looking at 5 days ago, 3, 4, 5 days ago, and that one. There we go. This is the real reason why I'm recording, right?
I think this is the 440 class.
Huh? No,
There was one
that's
before this that you clicked on.
no. This one should be the.
Should upload them with 310 Thursday.
Well,
You
that's-
used to, I saw, but then you kinda,
yeah, I have to change it manually.
yeah.
Yep. Yeah, I'm pretty sure this is the one.
Yeah, it looks like it.
Yeah, right at
And
the tail end of it, we had the overview.
okay, gotcha.
Yeah, I think
Okay.
that's where we left. We left on those 8 gates.
Okay, gotcha. All right, so we know where we are.
How to
Really
store
good.
data in bit 8.
Okay. All right, so this is where we are going to start today, is to kind of recapture a little bit of what we talked about last time. And then we'll move forward to actual memory. Okay, so I think this is the diagram that we were looking at. Maybe not this one, this one. There we go. So this is kind of important because it is a D flip-flop, okay, which means it can be used to remember 1 bit.
We run the one after this.
Did it? Okay.
Yeah, the multi-bit registers.
Yeah.
So the multi-bit is just a multi-bit version of this. It has the same control signals, but the data width is multi-bit instead of single bit. So that's the only difference between the picture before and this particular picture. So I'll just kind of remind you guys what each control signal means and what it does. Okay. So reset is only here because when you power up a computer or a processor, you need everything to be in a known state. And the reset is a asynchronous signal, which means it ignores everything else to make sure the content of all the D flip-flops get down to 0. Okay, so everything starts with 0. Enable is allowing you to specify which device should pay attention. And the reason why you need enable to specify who should be paying attention is because the D bus or the D line is shared between multiple registers. So when they're all listening to the D line, to the same D line, then you need to designate who should be paying attention. The clock line is specifying when the register should update. So only on a rising edge or falling edge, depending on the design of the D flip-flop, it's going to take a sample of what the D port is reading and then change its own Q port to the same state. So that's basically what we talked about last time up to this point. Is that okay? I mean, is that kind of consistent with how you remember? Okay, all right.
Is this how data is stored on your computer as well?
Hmm?
So this is how all the data is stored on the computer, right?
Not exactly. So RAM works differently, but it's a good question.
This is RAM, or is this?
This is what we call a register.
Okay.
This is what we call a register, and let me bring up.
So this would be like the hard drive.
Or
No,
the cache
no,
CPU.
With the hard
no.
drive,
It's not like a cache. It's called a register.
It's
So it's a very, very simple device where it can store multiple bits, possibly multiple bits, and it's got all of these control lines. So what we can do? Did we talk about the counter thing? I thought we talked about counters, right, in this class. So that's one use of a register. A register is a very low level device,
Okay.
and and it's not a memory device. It's not considered a memory device. When we talk about RAM, ROM, SSD or hard drive, it doesn't fall into those categories at all, because one register can only store 32 bits, 64 bits, or something like that. So we are not even close to talking about kilobytes or megabytes or gigabytes and stuff like that. Okay, but one thing registers are, okay, so let me go back to the counter example, because the counter example is kind of important in this discussion because it illustrates one particular use of a register. So this is the counter design that we talked about in this class. Does it look right to you?
Yeah.
Okay. So when you look at this, the register is right here, okay, which is kind of what we talked about, except now we look at the entire register as one single device instead of breaking it up into 8 individual D flip-flops. So we have got the enable. So the enable is always a 1 because this is the only register in this entire system. There's no reason why we cannot enable it all the time. The clock line is controlling when we want it to update. Basically when it updates, it samples the input line, which is the D port, and then it will change its own internal state and also change the output Q at the same time. The reset line is connected to 0, which means we're not gonna reset it. There's no mechanism in this particular design to reset it. And then this particular design just takes the output of an adder and feed it into the input of the register, and then the output of the register in return is going back into the input of the adder. So the idea is, when you control the clock line, every time you have a rising edge, the counter or the register is going to increment by 1. Because the input, if you click on the input, this is 1 already, but the register is not 1 because we are not experiencing a rising edge. And because there's no rising edge, the register is not updated. But the moment we click the clock line to create a rising edge, the register is going to update to a value of 1. Now, at this point, the output of the adder is 2 already, because the output of the register is 1 already, which basically completes the whole cycle. But the register is not updating because it is not experiencing a rising edge. So for each rising edge of the clock, the register will basically increment by 1. So is that okay? I think we kind of demonstrated this last time. I just want to kind of bring this up again to remind you guys what we talked about last time. Okay? Cool. So registers are interesting in some other ways too. There's such a thing called a shift register, which is not to be confused with bit shift operations that we have been doing with all the floating point number discussion. So a shift register is kind of interesting because in order to fill in the content of a register, you just need, quote unquote, 2 lines. You need a clock line and you need a data line. Okay? And using only 2 lines, you can clock in data into what we call a shift register. And the actual width of a shift register can be any width, but it only takes up 2 lines to control its content. And the reason why you can do that is because you are basically, it's kind of like a class like this, okay? So if I want to pass something, I just give you something, and then you pass it on to the next person. If I give you another bit, you pass on to the next person, but when you have your bit, you pass it on to the next person. So using this particular mechanism, I only need to give one person, repeatedly, different content, and by having a route of you guys, passing that the paper route in a class, I can now have one single person, but I can specify the content of multiple bits within the class. Now I want to talk about that just a little bit because I have the exposure to this thing here, which is a little bit out of the scope of this class, but I think some people may be interested in at least getting to know a little bit better. Of course, I cannot remember the name of that thing. Smart LED. I cannot remember the name. Let me look it up.
You can get a new sprinkler console for only $124.99.
This is, it's amazing. Okay, what this thing can do for how much you pay for it. So let me look up the name of that thing first. I received it over the weekend, but I haven't done anything with it yet.
Is this the sprinkler console or
No, this is an LED. It's a smart LED. It's called. Okay, come on. Okay, ALITOVE. ALITOVE Smart LED WS2812B. I should find it. There we go. This is really interesting. It's not this one, but it's a similar concept. But this one is available in individual, so it's not solder yet. Okay, anyhow. Okay, so if you look at this LED strip here, okay, there we go, magnify, no, go away. Okay, so this is a single strip of LEDs, okay, and you can kind of see that there's a whole lot of LEDs, right? But each LED, you can see that it has a rainbow color, right? And most people think that that's just how the LEDs are laid out, okay? Each LED has a particular color, and by selecting and putting the LEDs, where it is going to go on the strip, this is what it looks like. That is not the case. Each LED actually can be any one out of 16 million colors. 2 to the power of 24 is 16 million, okay? So the way you specify, and then the interface to this entire strip is 3 wired. You have ground, which is negative power, which is, and then you have 5 volts, and then you have a clock. Excuse me, you have a data line. There's no clock either. So the way you do it is you quote-unquote clock in, and so you basically clock in 24 times the number of LEDs in this entire strip. The first LED is going to capture the first 24 bits, but it will pass on whatever is left over. The second LED, from its perspective, is going to capture the first 24 bits. But that actually is the second 24-bit chunk from the perspective of whatever is sending the data to the entire strip. The third one, from its perspective, is capturing the first 24-bit chunk and passing on everything else. But from the perspective of whoever is transmitting the data from the beginning, this is the third chunk of 24 bits. So by using this cascading method, you can use an Arduino, okay, which is a very inexpensive microcontroller unit. You can use an Arduino to control and address each and every single LED by using only one wire coming out of the Arduino, which I think is really fascinating because it's easy. Yep.
So in like C++ terms, you pass it like an array. The first one takes 0, it passes 1, and then the second one takes 1.
Yeah, you have to look into the actual interface, because you can look up Arduino Smart LED library.
And there's only one Arduino for the whole thing, right?
Yep. Okay. Oh, it only uses up one line of an Arduino, so you are left with, I guess, 8 or 9 to do something else. Huh. So it's very interesting what you can do with this. I just kind of wanted to mention this because we were talking about registers, and this is a very special kind of register where you clock in the content of those registers 1 bit at a time, but because it has a serial nature, you just have to spend more time to clock in more data, and eventually you get to control each and every single LED of the entire strip, which is pretty long in this case. So if you want to make any type of display, this is one way to do it. I think there's a version of this where you can buy 100 individually addressable LED, not soldered onto anything, for about $16. Now you might say, well, $16 for 100 LED, that's kind of expensive. But if you think about each LED having 16 million colors to choose from, and you can daisy chain the whole thing in any shape you want, and you can control the entire thing using Arduino and only one output out of an Arduino, it is interesting, of all the things they can possibly do with this thing. You want to light up your bike in a certain way, that's how you do it.
What are you going to do with the lights?
I promised my kids that I would make a LED version of fireworks stuff for 4th of July, because we'll be in a not national park, but we'll at a campsite. So real firework would not be a very good idea. So but I bought 100 of these things.
$300.
No, it's actually, let me see if I can find that.
$3,000 worth of lights?
No, it's 100 LED for $16.
Oh, okay.
So it's very, very affordable. I cannot find that version. It just comes in individual LEDs. Okay. And they come in various forms too, not just surface mount, but it's just kind of cool, that they can do it. And for those of you who don't know what is an Arduino, look it up, and some of you may be interested. If you like to tinker and actually make things in addition to writing software, the Arduino and also the Raspberry Pi, those are really interesting project ideas. And they're both C programmable, C++ programmable, which basically means, once you have taken cisp310, you can program those things.
I saw a guy who once made a game. There was a dude I knew from high school who once made a Game Boy, homemade Game Boy out of a Raspberry Pi. It was really cool.
Nerd?
Yep.
Yeah, we weren't cool people.
Super nerd. Where I worked before, they called me Geekosaurus. And that's from the second geekiest person in the company. All right.
So that would make you the first then.
Well, I was also called one of 7.
They said 1. They said 1, and that means the first.
1 of 7 means that I have been there the longest. Yep.
Yeah. Whoever said that was probably the nerd. Whoever dubbed you that.
Alrighty. So, are there any questions about registers at this point? No questions? Okay, so getting back to not the modules, but getting back to the topics. There we go. So we just talked about the clock circuit because the counter is a clocked circuit. Okay, and the clock circuit requires edge-sensitive D flip-flops or edge-sensitive registers. So the next few topics are basically just quote-unquote study ROM in the Logisim library reference, RAM, and also MUX and DMUX. Okay. Have I shown you guys how to extract the HTML documents out of Logisim?
No.
Okay, so this will be a good time to do it. So normally, when you go to Logisim, let me go there first, and you can go to Help and go to Library References, and then you can look up stuff, right? But if you want to, oh, okay, it has just crashed. Okay, time to restart Logisim. Save. Okay. Let's see, where is that? There we go. So in Logisim, you can access its reference library through Help, and you can get to, basically everything that we need to use, like in the memory library. You can go to register, figure out how to use a register. You can go to RAM, figure out how to use a RAM module. Go to ROM and figure out how to use a ROM module. But this is not very handy if you want to print this out and bring it with you in the second exam, right? So one way to do this is to unzip the jar file. Okay, so let me show you how to do that. All right, so let me go to a terminal that you guys can actually see. There we go. This is better. Let's see. Do I have Logisim here? Nope. I do have it here. And I have a folder already decompressed, so I'm going to remove that first. Okay. So I'm going to remove Logisim as a folder. The first thing you will need to do if you use Windows is to rename the jar file to a zip file. Just change JAR to ZIP, okay? The reason why you have to do that in Windows is because Windows determines what can be done to a file strictly based on its extension. So a jar file, you cannot unzip it, okay? Because it's an archive file in Java, and the only thing you can do it is to run it as a JAR file. In Linux, there's not as much of a problem, but I'm just, I renamed it to, or copied it to logisim.zip already. Then the next thing you want to do is to make a folder, because if you don't make a folder first, it's going to be messy. So I go to the folder first, and then I unzip the zip file. There we go. And in Windows, you just double click on the zip file, and then you say extract all, basically doing the same thing. And it will extract a lot of files because it includes the source file of logisim. Within those files, within those folders, there's one that is named doc, DOC for document or documentation. Go to that one, and then you can also see that it supports multiple languages. So since I can only read English in this case, I go to the English version, and in here you will go to HTML, and inside HTML you will find your familiar index.html. That's where you need to go in order to access the individual documentation pages as a web page. Yeah. So let me show you how I can do that here. You just go to any browser, and then you specify what you want to open. I think it's file : something. Okay. So I just need to navigate to my folder. Okay. Go to Logisim. Logisim, there we go. And in here we go to doc, and then in here we go to en, and the HTML, and then index.html. Once you click it, it's a very simple looking page, but then you click library reference, and then you have access to all the individual components. Okay, so you can scroll down to figure out, okay, so let's say we want to look up ROM, read-only memory. So we scroll down, we go to ROM, give it a click, and this is the page. Now, because I'm opening this not within Logisim, but inside the general purpose browser, I can Control P and print it out. Okay, so you can do the same thing. So if you want to bring the documentation of some parts, to the next exam, this is how we can do it. Or if you say, well, I don't need the entire thing, I just need certain parts of it. Copy and paste it into a Word document or Google Word document, and then you can do your own editing. Then you can say, okay, I'm going to consolidate the notes to a condensed version to bring with me to the second exam. Is that making any sense? Okay. All right. Since we're here, we're going to talk about ROM. ROM, I'm just kind of surprised sometimes that it doesn't explain what a ROM is. It is read-only memory. Okay? So just to give you a brief history of ROM, there are different types of ROMs. Okay? Read-only memory is needed because when you first start the computer, your RAM or random access memory is blank or random. So your program, there's no quote-unquote program to run if you don't have any ROM. So that's why when you first start up the computer, the firmware or the BIOS, or the bootstrap, portion has to be stored in read-only memory in order for your computer to know what to do when it first starts up. Okay? So typically ROM would access these days, your hard drive or SSD, go to the boot sector, which is the very first sector of the entire hard drive, read some more instructions, execute it. That in return it will bootstrap another part of the operating system, the bootloader, and then that will bring a small version of the kernel, and that in return will bring the full version of the kernel.
So ROM, it would be on your hard drive, but just partitioned into read-only?
No, ROM is a chip basically on your motherboard.
Gotcha.
So it comes on your motherboard.
Gotcha.
Now these days we don't use ROM anymore. Okay, the term ROM is kind of not used anymore. So I'm going to give you a quick, brief history of ROM. So ROM is originally, it is just the content of ROM is determined in the factory. So by the time it is shipped out, it is pre-programmed and it cannot change. Yep.
It's basically System 32, isn't it?
Is what?
No.
System 32?
No, it's not.
System 32 is a part of the operating system. So by the time you get to System 32, it's really late in the bootstrap process already.
Okay.
Yep.
Lookup tables are basically this.
A lookup table, you can use ROM to make a lookup table, yes.
Okay.
Yep. So the original ROM, is read-only memory, and the content is determined at the factory. Okay, so if you want to manufacture a device that makes use of a ROM, you have to send the specification of the content to the factory or whoever is manufacturing the ROM and say, okay, I need 500,000 of these things. Okay, because it doesn't make sense to say, oh, I just need 5 of those things, because they have to reprogram their machinery in order to program the ROM. And once you program these ROMs at a factory, they cannot be reprogrammed again. So you can kind of imagine that is kind of inconvenient, because what if the first version of your firmware is buggy and you just fix something, right? So you have to ship out the corrected version to your customers, and that becomes a problem if you have to wait for the manufacturer to manufacture the next batch to you, and then you in return ship it out to your customers. So that's why the second generation are called PROMs. P stands for programmable. So programmable read-only memory are chips that are blank to begin with. So they ship it to you blank with no content in it. And then you buy a special device to program it. But it is one-time programmable. So that's why a lot of times, these days, back in those days, they don't use this term, but you can kind of imagine there's an OT in front of the P, which stands for one-time programmable read-only memory. Because once you program a PROM once, that chip can no longer be reprogrammed. It can only be done once. And the reason why it can only be programmed once is because the programming process is actually burning fuses on the chip itself. So it's actually disconnecting certain connections within the chip by quote-unquote burning certain connections off. And that's why you cannot unburn a connection. Once a connection is burned and disconnected, you cannot get it back ever. So that turns out to be better than ROM, okay? Because now you have the capability of correcting a mistake in a firmware. Send out the prompts to your customer and just say, okay, pull out that chip and put in the new version, and it's going to be okay. But it's kind of wasteful because the prompt that they pull out of the circuit board is no longer useful. You just throw it away. So the next generation are called EPROMs. E stands for erasable. So now we have erasable, programmable, read-only memory. That should sound really confusing. So the erasable ones look like this. So it's a chip, rectangular in shape, pins coming out from both sides, and this one has got an optical window in the center. Usually it is round in shape. Occasionally it is kind of rectangular in shape, but doesn't matter. It's an optical window. The erasable part uses UV, ultraviolet, to shine onto this portion, and then the UV light, now that part I never really got, but the UV light can reset the content of the ROM so they can be programmable again. It has a cycle limit of maybe a few hundred times, okay, and each time it takes about 15 minutes with intense UV in order to erase the chip. So it is slightly better because now, all the ROMs that are kind of old, outdated and whatnot, you can collect those back, erase all of those, and then reprogram those and use them again. The next generation adds another E to it. So we have double EPROM. So double EPROM, the first E stands for electrically. So it is electrically erasable, programmable, read-only memory. So with those chips, it is just a regular chip. Okay, there's no optical window anymore. To erase the content, you have to put it onto a special programmer board where they use a different voltage to erase the current content so they can be programmed again. Okay? Is that okay? Yep.
What's the practical application of making it read-only, or is that just a limitation of the chip?
No, it is an intentional limitation because that portion, Okay, to use today's term, okay, so that you don't break your device.
Okay, that's what I assumed, but I didn't.
Yep, yep. So that you don't break your device because there's a certain core portion of your phone that is not writable. It is only readable. So no matter how much you screw up, Android and the whole thing, at least you can get to the part where you can bootstrap again. Yep.
Right there it says the ROM component stores up to 16,777,216 values. But that's not bit 2 though. What is that? What's determining that?
Okay, that's specifying the number of locations. So
Okay.
when we get to it, we'll read what it means by 16 million. 16 million of what? So it's basically the number of locations that you can have in a ROM in Logisim. So these limits are specific to Logisim only.
So it's not bits, it's not different values, it's total values.
Locations. I would look at these as locations. So forget values, substitute it with locations.
Total though is the right word, right?
Right.
Okay.
And then
so it's
each
not-
location can be 1 to I think 32-bit wide. So we'll get to that part. But getting back to the history here. Okay, so we're we're traveling with a TARDIS at this point. So the next one is something that you already know. It is flash memory. So the difference between double EEPROM and flash memory is depends on which generation. But double EEPROM tends to be very slow in terms of reprogramming it, and occasionally you need a different voltage for erasing it. And also when you erase EEPROM, you erase the entire chip. You cannot just say, oh, I just want these 16 bytes gone. Nope. Whenever you erase, the whole thing is gone. Okay? Flash memory is based on a little bit of that technology, but flash memory has two main differences compared to EEPROM. One, it doesn't need a different voltage anymore, which means your circuit board, your device, doesn't need to have some special power supply just to erase the content of ROM. And then the second one is in flash, it comes in sectors, so you can erase and overwrite by the sector. And the sector size tend to be pretty small. They range from 128 bytes all the way maybe to kilobytes at the most. So when you have a large flash device, you don't have to erase the entire thing if you want to reprogram just a portion of it. Is that okay? And then the next one that comes along, would be, so using flash, you can implement solid state drive. But the solid state drive is interesting because when you look at the solid state drive, most people look at it as if it is just a dumb device. Oh, it's just a drive, right? That is not the case. A solid state drive is a computer on its own. Okay, when you power up the thing, it is an actual computer. Now, why do we need a computer to do just solid state drive? One problem with flash is each sector has a limitation of how many times you can overwrite it. That is the biggest problem of flash memory and to SSDs as well. So do you guys know how many cycles, today, using today's technology, how many times can you overwrite a sector in SSD before that sector is quote unquote burnt out?
A few million, right?
I think it ranges in the millions.
A millions? Okay. So millions sounds like a big number, but it's not. If you think about your serial ATA bus, how fast you can send data to a drive. If you intentionally want to burn out something, it doesn't take much time. So that's why with SSD, it is actually doing its own what we call load balancing. So it would actually it actually has more sectors than the size that it reports as. So let's say you buy a 1 gigabyte SSD. Okay, the actual amount of storage may be 1.2 gigabytes. Okay, I don't know how much margin they leave, but it's actually more than that. And the reason why what they need to do that is because they know sectors will burn out. Okay, so what they do is they remap sectors. So the physical sector here may actually be something else when you address it from the serial bus. The controller on the SSD itself is managing all of these things to give you the best longevity out of the device. Yep.
I think it's the other way around where they report the max size, but when you open up the drives,
Oh, this is
it's
the other way
actually-
around?
Yeah, it's actually
Okay.
less than what you display.
Okay.
It's
or
less.
less than what you actually buy. So when they say you're getting a 1 terabyte drive, you'll actually get 960 gigabytes, which is what I have right now. Like it was less.
Okay. So anyway, so there is a difference. They save some of the sectors, to be used, when certain sectors are burned out. You don't throw away the whole drive. You have a certain amount of time before you burn out enough that the SMART technology will report to your operating system and say that, oh, this drive is near its lifespan, it's time to replace it. SMART, S-M-A-R-T, is an acronym for in hard drive technology. It allows the controller on the drive, not just SSD, but also traditional mechanical drives, to communicate with the computer to report back the expected life expectancy of the drive. So it can just kind of say that I'm about to fail, it's time to replace me, and give you warning ahead of time. So you might want to, this is practical from a practical standpoint, so when you get home, okay, don't do it during class. I know some of you are going to do it anyway. Check out programs that can read back the smart data from the hard drive, and it will report back like how many hard errors it has encountered. It will report back what is the expected longevity of the drive, how many hours it has been used, and so on and so forth. It's really interesting because you can actually get to know that your drive is close to its end of life, before it actually starts to crash. Then you can replace it in time and not lose any data. Question?
How often does a drive? How often does a drive?
You're becoming like me. Yep. Go ahead.
How long does a drive usually last?
I'm not sure whether this is still a good measurement or not. It's mean time between failure. Mean time between failure. MTBF. So this is but this is during normal operation. Different types of drives degrade differently. Like a mechanical drive, the spindle is usually the problem because the spindle it's basically just a single point, okay? Because there's bearing, but very few type of mechanical bearing design can handle 10,000 RPM and almost on all the time. So that usually is the limit. Is when that starts to go, your drive will start to wobble, and then things will just kind of go south at that point. You can also have particles getting into the drive. In the good old days, the quickest way to kill a drive is to blow smoke at it, because smoke particles is actually pretty big compared to the gap between the disk head and the platter. The disk head is floating on the platter on a cushion of air. And not even dust, a smoke particle is big enough to crash the head. But with SSDs, the biggest reason why SSD drive would fail is one, temperature. Okay, temperature kills just about any semiconductor electronics. But the second reason would be overwriting a sector too many times. And this is also one reason why you should not or don't want to use file allocation table, otherwise known as FAT32, on an SSD, because FAT32 is a file system that has one single or a few sectors that are overwritten all the time. It would just kind of kill the drive quickly because of that. NTFS is okay, extension 2, 3, 4, in Linux is fine. The file system in Mac OS X is fine, but just don't format it to FAT32 because it will kill your drive prematurely.
That's why they said don't defrag the drive if it's an SSD.
Yeah.
In an SSD, defragging doesn't really do anything because defragging or fragmentation is a problem only on a mechanical drive because your file is now scattered all over the place. It's not lost, okay? It's just that in order to retrieve the entire file, you have to go to different tracks and then different sectors on the track, so it takes a lot of time. Because in order to move the head, it has a latency, which is measured in milliseconds, and then once you get to the right track, waiting for the rotation, waiting for the sector to rotate under the disk head takes additional time. So to you and me, it's just a few milliseconds, no big deal. But when you need to do that to multiple sectors and your computer is capable of doing billions of instructions per second, it's a huge amount of time. It's a huge waste of time. But SSDs don't have that problem because it doesn't actually have physical tracks nor sectors on the track. So when you have your file fragmentation on an SSD, it doesn't do a single thing. If you defrag an SSD, it actually uses write cycles of the sectors unnecessarily. So this is just me, but according to this logic, it doesn't make sense to defrag an SSD. It would actually kill the drive prematurely. Has anyone heard of anything like that? Yes? Okay. So I'm not insane.
No, it's.
Well,
I don't even
on,
think you,
on this subject matter,
I
I'm
don't even
not.
think you can. You'd have to I don't even think it gives you the option to defrag it when you go to try. It does.
Yeah, but it doesn't help with performance, but it kills the drive faster, because you have basically massive rewriting on the sectors unnecessarily. But I think the smart technology can identify what kind of drive it is. So the operating system can say, hey, you have a SSD, it doesn't help you to defrag the drive, so it may not give you, it may give you recommendations like not to do it. I don't use Windows, I cannot tell. And I don't have an SSD on my laptop either, so.
You're clearly a Mac type of person.
No, I'm a Linux kind of person.
An Apple, definitely.
Okay, so we kind of sidetracked a little bit, but that's kind of the history of everything starting from ROM all the way to SSD. Your cell phone still has ROM, okay? It still has either ROM or PROM, because unless your device can be bricked, B-R-I-C-K, okay, bricked.
What?
Okay. How many people mod your phone because I just want to run my own version of whatever, right? So on certain types of phones, okay, you can overwrite enough of the phone, like the really low-level stuff, to the point that your phone can no longer recover. But it's the design of the phone. Some phones, always has a fail-safe. You can only overwrite up to a certain point, but there's always something that cannot be overwritten because it is not erasable, it's not programmable. So you can always have a fail-safe, stage that you can restart the phone from. So, but certain phones don't have that fail-safe. So with those phones, you can overwrite portions of your phone to the point where it cannot be recovered anymore, and it is said to be bricking your phone because you're turning your phone into a brick. Now these days, of course, a phone is more like a tile than a brick, but you get the idea.
Not even, more like a leaf.
Well, actually, with some of the larger phones, especially tablets, it makes a pretty good cutting board. Gorilla Glass, are you kidding me? That's pretty tough stuff, right? Why are you using my iPad as a cutting board?
It's all good for it.
Expect me just to quit Angry Birds just like that? Can do
Okay.
two at the same thing. Two at the same time.
All right, so if that is what a ROM is, okay, historically this is what a ROM is. So now we want to know, okay, so how do we make use of a ROM module or component inside LogicSim? It only has got 3 ports. One port is designated A for address, one port is designated D for data, and one port is designated SEL for select, okay? So select is kind of a way to tell whether this ROM, whether it is addressed or not, okay? Am I talking to you? The best way to look at this, not including cell, is address is the index, okay? The stuff that you put inside a square bracket when you try to access an element out of an array. That is what the A line is doing. The data is basically the value of an element in an array. So in other words, each ROM is like an array where the A address is the index and D is the value of the addressed or indexed element inside the array. Is that okay or not? Okay, let's go ahead and run an example. because I have one already done, so we can just use it. Okay.
Is this what we're doing in the lab?
No, we are doing a positive exponent for the floating point stuff in the lab. And that one is ROM example. There we go. Okay, so I have two ROMs here, but just ignore the two part. We'll focus on the top one, okay? So with the top one, okay, let me click it first so you can see the properties of that ROM. So when you look at the top ROM, there are only three properties associated with a ROM. One is the width of the address bus. In other words, how many bits do you use to specify which location you want to address? So in this case, I have 3 bits to specify which location I want to address. Now, I can have 20 gazillion locations on this ROM, but it wouldn't be useful because with 3 bits, I can only specify location 000 all the way up to location 111, so 8 locations altogether. Does that make any sense? So when you specify the address bit width, you are also going to specify the amount of locations on that ROM. It is 2 to the power of the address bit width. Is that okay? The second thing is called the data bit width, which is controlling the width of the D port. That in return specifies for each location, how many bits do we have for each location. In this case, for whatever strange reason, I pick 5 as a really odd number, but you can change that. So when you click the drop-down box for data bit width, you can see that you can specify anything all the way up to 32, but I'm just using 5 here. In terms of the address bit width, I think you can go all the way up to 24, and therefore the 16 million something. Yep, there we go. So if you specify 24, then you have 2 to the power of 24, which is approximately 16 million locations. So I'm going to stick this with, continue this with 3. And then this one is content. So if you click the content, then it will open up an editor where you can specify the actual content of this ROM in hexadecimal. Is that okay? Are there any questions about what I just talked about at this point? Questions? Okay.
With the content, so it's all on one line, or is that what I saw? All the information was just on one line?
Only because the editor itself prefers to format in a way where each line has 16 locations. So we only got 8 locations here, so it's not going to fill up even the line. If you specify anything that needs more than 16 locations, then it will have 16 on each row, and then it looks slightly different. Okay. All right. So let's go ahead and check out the bus at this point. Okay, so the input pin 000 is 000. Okay, so that's not surprising, but it should be outputting whatever content is at location 000, which is 12 in hexadecimal, but it's not. Instead, it gives me all the X's here. What do you think that means?
Select's not on.
It is not driven. Okay, it means the bus or these wires are not driven. Now, to understand that part, okay, all we have to do is to draw a wire that is not connected to anything. So let's see. Can I draw a wire that doesn't connect to anything?
The point tool?
No, I can trick it to do it.
Yeah.
So I just draw something like this first, and then we go back and erase the pin. Now we have a wire that doesn't go anywhere. And then we can check the state of that wire. It's like, okay, what is on this wire? And it's a dash. Okay, basically saying it doesn't make sense, but in this case it's an X, which means it is not known. We don't know what it is. Okay? Okay. So what this means is these wires, okay, there are 5 individual wires within this bundle, and neither is quote unquote being driven. What do you think that means?
It's not being told to be on.
Yeah.
Exactly. Nothing is specifying the content on those wires. Okay? Now, the reason why nothing is specifying the content of those wires is because select is off. I'm telling the ROM, just be passive, don't do anything. Okay? So when I turn select to 1, the ROM would wake up, it will pay attention to the address line, select that location, and then output the content of that location to the D port. So let's take a look. Okay, so you can see that the moment I turn on the select, it highlights which location is being addressed. But when I click on this wire, you will see the content of that wire as well, because it now has content. It is not driven anymore. Now it is driven. So the first part should not be surprising, the binary part, because 12 as a hexadecimal number is 0001 0010. Okay, but since each location only has 5 bits, the most significant 3 bits are just implied. They're actually not stored in the ROM, and that's why we only got this 1 and then 0010. Is that okay?
Did we already look inside the ROM?
Hmm?
Did we already look inside that function, or is it just implied that it does that thing?
What do you mean by look inside?
Like we saw what was in. How does that function? Was that just a series of registers?
This has nothing to do with registers. Yeah.
No, the AD select that box.
Yeah, this box. What about it?
That's the ROM, right?
Yes.
And then we already see how the inside of that worked. Was it, or is it just implied that it does?
We have not seen how the inside works.
Okay.
Yep. So I can change this address bus. If I turn this 0 into a 1, what do you think is going to be the output?
It's going to be 02.
It'll be location 010, which is location 2, and what is at location 2? 0F, which means the output is going to be 01111. Correct, because the most significant bit is a 0, and then the least significant 4 bits are going to be 1s. Okay, well, let's check it out. We want to make sure that that is the case, so click it, and you can see how this location is now highlighted because it's selected. Because the address bus, remember, this is what you put inside the square bracket, when we use array indexing as an analogy. Okay? And then when we click this wire, we can definitely tell that it's 01111 and the value, and then /15. What is the /15? It's the signed decimal value represented by that bit pattern. But 01111 being 15 is not really surprising, right? Because it is 1 plus 2 plus 4 plus 8, and that turns out to be 15. Cool. So I'm going to throw a wrench into this whole thing, turn this back into 0, and then look at this wire again. This is -14. Why is it -14? It's looking at the 5 bits as a signed integer. It's a 5-bit signed interpretation. Okay, the most significant bit is always the signed bit. Is that okay? So we have 1, 2, 4, 8, and this is specifying -16. So we have -16 plus 2, and that turns out to be -14. So it does make sense, okay? Now, if you're not convinced that 10010 should be representing -14 as a 5-bit number, apply 2's complement to it. You should get 14 back, or the binary bit pattern of 14 back, because 2's complement is supposed to negate the sign of the number. So if 10010 is representing -14, then the 2's complement of the same bit pattern should be 1110, which is representing 14. It's a 4-bit number. Okay? Alright, cool. Now we have a second ROM, right? Look at this bottom second ROM. And we're going to pick a location where things are agreeable between the two. Okay? So I'm going to specify location 11 with the bottom ROM. If I specify 011 as the address, which location is being selected? 011 is location 3, and location 3 has a content of 12 in hexadecimal. Okay, and that should be the same as the one above, right? Okay, so let's turn on this ROM and say, okay, ROM number 2 or bottom ROM, now pay attention to the address line, and we want you to output as well. Okay, not a problem. The output, which is shared between the two, is 10010. Cool, nothing is problematic.
What happens when they disagree, though?
Aha! That's exactly what I want to go to. Okay, very good. I like those discussions where you guys are leading me. Let me turn off the top one first. And I will select location 1, which is the 0, 2, right? So they will be off by 1 bit. The most significant bit is going to be different. The top ROM would say the most significant bit should be a 0. The bottom ROM says the most significant bit should be a 1. And they are both sending outputs only. It's not like one is the output, one is the input, where it's okay. Both are now trying to drive the wire. One is saying this wire should now be a 1. The other one is saying this wire should now be a 0. Yep.
Would it function like an OR gate?
Nope. Nope. It is going to give you some. Okay, so let's check out what logic sim is going to report this problem.
It's gonna be like an AND gate, I think.
Nope. It's not a gate of any kind. It is a problem. It is an error. So when you click on the red wire, it tells you that there's an error, and the problem is with the most significant bit, because one device wants to turn it into a 0, the other device wants to turn it into a 1. So now we have a problem. Okay. So logically, you cannot have the same wire being both 0 and 1. This is not a quantum computer. Okay. But physically, what's going to happen?
Wouldn't it function like an OR gate physically because it's outputting 1 to this
Nope.
side?
This is technically called a bus fight.
It's only
Yeah, that's a technical
the
term.
same.
It's called a bus fight because now you have one device trying to turn it on, one device wants to turn it off, right? Okay, so I'm going to draw this picture. I will draw it on the whiteboard because it is not going to be in a quiz, okay? But I do want you to kind of look at it this way. Okay. Remember this picture?
That's the NAND gate, isn't it?
Yep, it's the NAND gate. And remember, everything can be done with NAND gates, including ROM components, okay? So I'm just going to draw this picture to represent one side, the top one. I'm going to draw another picture like this to represent the one at the bottom. Okay. Okay, and we have 1, 2, round. Okay, all right. So the scenario is kind of like this, okay? The top ROM, okay, is specifying a 0, which is basically saying, we are connecting these two. Let me be more specific. So we are having 1, 1 in this case, because 1, 1 as the input will connect the two N-channel transistors, and therefore, this path, there's a path from here to ground. Is that okay?
Maybe 0.
That's representing the top ROM, which wants to turn this wire to a 0. Is that okay? The next one is representing components of the bottom ROM, which wants to turn it up high, right? Okay, so using the same schematic, here, we can say it has 0, 0 as the input, because we know that when you give a NAND gate 0, 0, the output is supposed to be 1, which means this wire is connected to power. Okay, so let me use the red wire to indicate how the outputs are connected. This output, representing the most significant bit of the top ROM, has a way, right here, has a way to connect. Oh, that's not the output. Okay. Excuse my drawing here. That is just the gate. That is just the gate. The actual output is from here. That is the actual output. But it does have a connection to ground, like that. Is that okay? The other one, on the other hand, has a path. In fact, it has 2 paths to go to high voltage. Is that okay? So this one is corresponding to the top ROM. This one is corresponding to the bottom ROM. And they're connected to the same wire. So we are basically saying this wire and that wire are now connected. What do you think is going to happen?
Power going straight to ground.
We have a large, quote unquote, large amount of current going from power through the P transistors, the wire, and the N transistors to ground. What is stopping the current to become quote-unquote infinite? There are a few things, but yeah, I'll let you guys name a few things. Is power, positive voltage, negative voltage. So when you connect something like this, what is limiting the current? Resistance, exactly. So there's resistance associated with the transistors. So when you look at the transistor, it's not a perfect switch, okay? It is not a lossless switch. There's always a little bit of resistance here, a little resistance here, and also here. The resistance is what is limiting the current to a certain amount. Is that okay? Okay. What is I current times resistance? Voltage. Very good. And what is voltage times current, assuming it is going through the same component? Power. Very good. So that means when current goes from here through the resistors, through those resistors to ground, we have some key values associated with each transistor. Does it make sense?
Wouldn't that make power just equal to this?
And what do you think that power is manifesting as in physical world? I mean, power or energy cannot be destroyed. Energy has to be conserved. So we are expending energy. The rate of expending energy is power. Okay, so it's only a matter of how much time do we use to consume, how much energy. So the question now is, where is that power? What is the form of that power, that energy?
Electricity.
Heat. Okay, so we're heating up stuff, right? We're heating up this transistor, this transistor, this transistor, and that transistor. But when you look at power and you substitute what is V, it is I squared R, right? So which transistor needs to dissipate more power now has to do with its resistance. Whichever resistor has the highest resistance will have to dissipate more power. What do I mean by dissipating power? Getting rid of power, right? Getting rid of heat. There's a certain limit of how fast heat can be dissipated when you have a chip that has a packaging on top, blah, 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 blah. You're not blowing a hot, you cannot get rid of heat really fast. So this is a good time to bring up another video from YouTube.
Just ask the astronauts.
Huh?
In space, it's almost impossible to get rid of heat because there's no atmosphere.
You can only do it by radiation in outer space.
Which is incredibly ineffective.
And that's why lasers make no sense. In outer space, laser railguns and stuff like that, all of those require a lot of heat dissipation in order to fire the second shot.
The Apollo astronauts, they weren't limited by how much oxygen they carried. They were limited by the big block of ice in their backpacks that was melting over time, because that was what was keeping them from overheating.
Okay, so this is a really cool video. How many people have seen this one before? Some. Okay. Okay, so somebody is running a benchmark test on a motherboard. So benchmark tests tend to run the processor pretty hard, okay, because they're trying to find out which processor is the fastest. Makes no sense to kind of let the processor idle, because that's not how you find out how fast a processor is. So they report back like the clock rate and stuff like that, and the heat sink is not even turning. I guess it's not even hot enough to require the fan to be blowing. But it's a pretty huge block, huh?
I think they just unplug the fan.
They just take out the fan, and then what happens?
Oh.
Okay. So let's pause right here. Okay, so there's a slow motion. So most of you probably think that it blew up, right? As in upward like that, right? Okay. That's not exactly what happened. So let's take a look. They changed the angle of the camera. It blew a hole on the table. In other words, it turned a processor chip into a shape charge.
Wow.
Don't tell anyone.
So you're telling me
It's on YouTube, okay? It's on YouTube. So next time you see somebody taping a motherboard on the window of an airplane, you know what to do.
So you're telling me all those NCIS hacking scenes are totally accurate when the computer just miraculously blows up in their faces?
It became a shape charge, and it's all because of the heat not being able to be dissipated. The heat sink is gone, which means the only way or the only efficient way for heat to be dissipated through the fans into air is gone. So all that heat has nowhere to go, and it just blows up. Okay? What do you think an explosion requires? Now, I don't want to turn this into a bomb-making class, but physically, what is an explosion?
Lots of pressure in a small space.
Gas. Not necessarily oxygen, just gas. Okay, high pressure gas. Okay, and whether it can blow a hole like that depends on whether you have actual physical material that is being pushed by the air. Okay. But where's the air coming from? Because in order for an explosion to happen, there has to be air that is pressurized, right? Highly pressurized, some kind of gas.
You don't need more.
Where do you think that gas is coming from?
From within. You don't need more air. You just need to heat it up a bit.
Yep, exactly. Your chip, the semiconductor material, is getting so hot that it becomes gas. It is vaporizing itself. Okay.
How quick does it take to vaporize?
And that is how you kill a computer. Okay, is to have a bus fight like this, because this is called a fight because it is now a matter of who is having the larger resistance. Whoever is having the largest resistance in this path dies first. Now, the good thing is, well, I'm not sure whether it's a good thing or not, but whatever dies first is saving the other one, because normally when a transistor dies, it becomes an open circuit, so it doesn't conduct anymore. But in this case, if the ROM is dying, okay, your computer is useless. There's no use of that computer anymore. So this picture explains the whole thing about driving, okay? Because now with this particular circuit, there's no way for it not to drive, so I cannot show you the circuit of not driving, but driving means that you are specifying, you're intentionally trying to change the wire to either a 1 or 0, a positive or a ground voltage. A wire that is not connected, okay, just imagine that I physically use laser to cut this wire, okay, and I cut it also here. Then this section of the wire is said to be not driven anymore. It's just a wire on the circuit board. It's not doing a single thing. Is that okay?
So connected means driven.
Connecting to something okay, if it goes through something that is of relatively low resistance to either power or ground, it is driving the line. So it can either drive it high when it is connected to power, or it is driving it low if it is connected to ground. But the resistance has to be relatively low in order for us to use the term driving. Because there's also pull-out resistors. So with a pull-out resistor, it looks like this, where you have a pretty big R here. Now with a big R, you would think, oh, it's going to blow up the resistor. Well, that is not the case, because when your resistor is in a range of 10 kilo ohms, then the current gets so small that it doesn't heat up anything. So it's basically, this is kind of like a weak spring. It is basically spring loading a circuit and say that if nobody else is driving it, it's going in one direction. But it's very easy for something else to overpower and turn it into a ground, turn it into a 0. But we are not going to talk about this because this is not a circuit class. 10,000 ohms is basically a pretty large resistance, because the amount of current is voltage divided by resistance. So even at 5 volts, if you divide 5 by 10,000, it becomes a very, very small amount. It's like 0.5 milliamps, which is a very, very small amount of current.
That's not enough to stop your heart. So
well, it all depends on how big the resistor is, because with tiny little resistors, it can heat up really fast, just because it doesn't have a whole lot of area to dissipate the heat. But this is a very interesting video because it really kind of illustrates, why, how much power is being dissipated. Now this is back in the good old days when the power dissipation of processors are upwards of 200 watts. These days, with our newer, smaller transistors, they don't run as hot anymore. I think the highest power consumption processor in production was the Pentium 4 line on the Intel side. They were basically close to 200 watts, but not really doing a lot of processing. So are we okay so far with all of these things? So I'm kind of tagging along a lot of things that are not exactly related to assembly language programming, but it is still related to the organization of a computer, because this is exactly what is happening when we have a circuit that specifies something like this. Is that okay? So to avoid a situation like this, you just have to turn off one of the two ROMs, because if one is talking, the other one is not talking, then you don't have this scenario anymore, because you only get one side driving the bus, but not both sides driving it. So there's no way you can have a bus fight when you control the select.
No one wins in a bus fight.
Hmm?
No, I'm kidding.
It really is called a bus fight. You can look up that term. Okay. So circuit design bus fight. But okay, they use a slightly more polite term, bus contention.
I was hoping I was hoping it was gonna be two people dueling on buses, school buses.
They say in that boxing movie you could have been a contender.
The school bus versus the city bus.
Because contention is too polite. Contention usually does not end up in death.
And this bus is gonna blow.
Yeah, but a bus fight you typically would damage components. Now, don't expect anything spectacular, because the transistors are so small, and you're not blowing up all the transistors. You're blowing up a very small number of transistors, just enough to make your computer not work anymore. This is the kind of things that happens when people design a motherboard or design the circuit wrong. But these days, it is interesting because we defer a lot of connectivity between the components to programmable logic parts, okay, CPLDs, FPGAs, and so on and so forth. So if those things are programmed incorrectly, we can still end up with situations like this, which is kind of interesting because you can actually send an update to a mobile device that will physically kill it if they design it incorrectly, and allow bus fights to happen when the CPLDs or the FPGAs are incorrectly programmed.
Knowing Apple nowadays, they probably would.
Well, it probably won't blow up, but it will basically kill enough of the components that it won't function anymore.
And then you'll have to update.
It'll be a brick.
Yeah, exactly. Now
Then you have a tile.
You
have a tile. Don't tile your phone.
Aren't they on the iPhone 10 now? It's ridiculous.
No, it's an X.
X? Oh, they even gave up. Now they're going on the route with Roman numerals.
They have always done that. OS X, OS 10.
OS 10.
Yeah, they always go for the Roman stuff.
Because it sells better. Oh, man.
Yep.
Which is why I keep buying Final Fantasy games.
So are there any questions about everything that we talked about today?
17.
No questions? Okay. So on your own, before Wednesday, I want you guys to read ahead of me so you read about RAM. So the only difference between RAM and ROM, which is kind of minor, but it's also major, is RAM is random access, it is read-writable. So that is interesting because we need an extra pin to specify, are we going to write to RAM or are we reading from RAM? That is just kind of natural. You need one more wire to control what is the function of the chip. But it also makes the data bus very interesting because the data port is not an output port anymore. Sometimes it's output, sometimes it's input. When you're writing to RAM, the D port becomes an input port. But when you are reading from RAM, the D port becomes an output port. So that is an interesting part of using RAM is the D port is bidirectional. It can go in either direction. So I'm just trying to get back to the class site so I can show you where we are and what I want you guys to read between now and... Okay, so between now and Wednesday, I want you guys to read the RAM reference manual, and also what a mux and a demux is. Yep.
Do we have to do all that HTML nonsense when we go into the server and put all that?
Well,
practice.
that's a convenience. Okay, if you want to access those individual HTML documents so you can print them, that's what you need to do.
Well, you can get them off of there as well.
Oh, yeah, absolutely. For Wednesday, you don't have to print it out.
Okay.
Yeah. Okay, so we're heading out to the lab and do the positive exponent part of floating point conversion.
Question: we recorded the answers to the exam, right? When you went over.